Okay, so here is a polynomial, and the goal of this is to find all the roots. When you're done with that, classify them as integer, rational, irrational, or complex. So the first thing we do is we use the rational root theorem, which gives us a list of possible rational zeros. So we find the factors of the constant term, which is plus or minus 1, plus or minus 2, plus or minus 4, and the factors of the lead coefficient, which is plus or minus 1. So I divide these, I get plus or minus 1, plus or minus 2, plus or minus 4. Then I use the remainder theorem and factor theorem and see if any of the remainders will be equal to 1. So this is really just a calculator exercise. So I'm just going to plug these into the calculator, so let's get that started. The function is already plugged in there. Make sure that my table set is my independent set on ask. It doesn't care what, I don't care what your initial table start is and your changing table is. So we go to table and we do 1, -1, 2, -2, 4, and -4. So we want to write this list down back in our example. Okay, so we know that 1 is a root, so therefore I can use synthetic division, divide this cubic down to a quadratic, and either factor it or use the quadratic formula. So I put 1 in the corner, write down the coefficients of the polynomial in descending order. 1 comes down, I multiply 1 times 1 is 1, I add those, I get 2, 2 times 1 is 2, -6 and 2 is 4, 4 times, excuse me, that's -4. 1 times -4 is -4 is 0. So I get x squared plus 2x minus 4 is equal to 0. There's no factors of 4 that give me 2, so using the quadratic formula, I get -2 plus or minus the square root of 2 squared minus 4 times 1 times -4 all over 2. I'm going to simplify this piece right here. And now, there's a perfect square that divides into 20, and that would be 4, so I can rewrite this as -2 plus or minus 2 square roots of 5 over 2. Since all of these parts are divisible by 2, I can divide everyone by 2, and I get -1 plus or minus the square root of 5. So 1 is an integer, and -1 plus or minus the square root of 5 is irrational. Okay, so again, we got to find all the roots here. So the first one we're going to do is the rational root theorem. So my p-values are plus or minus 1, plus or minus 2. My q-values are plus or minus 1, plus or minus 3. So I find the quotient of each of these. So plus or minus 1, plus or minus a third, plus or minus 2, plus or minus 2/3. And then evaluate f at all these 8 values here. Okay, so here are the 8 values I need to evaluate, so let's go to the graphing calculator. I've already plugged it into my y equals, so now I go to table set and make sure that my independent is on ask. I go to table values and I get rid of what is already there, and so I plug in all the values. So that would be 1, -1. I guess you can just watch me. Okay, so here's 7 of the values here, and then I just need to do one more, which is -2/3. So -2 by 3 is equal to -3.11. So I got to write these values back on the previous page. Okay, so it looks like we actually have 2 roots in this scenario. We have 1/3 as a root and -2 as a root. So shown in the previous example, it doesn't matter which one we choose first. I can choose the 1/3 or the -2. It doesn't really matter. Let's do the synthetic division now. So this, by the way, was the remainder theorem and the factor theorem. So I'm going to do 1/3 into 3, 8, 6, 3, -2. So 3, 1, 9, 3, 9, 3, 6, 2, 0. And the other one is negative 2. So it's negative 6 is 3. 3. This is negative 6 is 3. Negative 6 is 0. So this is a quartic down to a cubic, so this is a quadratic. So I get 3x squared plus 3x plus 3 equals 0. I'm going to divide everything by 3, which is perfectly legal. And now I have this thing here. There's clearly no factors of 1 that give me 1, so using the quadratic formula, I get negative 1. And I simplify this underneath the radical here. I get negative 1 plus or minus the square root of 3 all over 2. And that gives me negative 1 plus or minus I square roots of 3 over 2. So this root is complex. 1/3 is rational. Negative 2 is an integer.